Once we've made a bunch of measurements, typically we're going to take those measurements and put them into mathematical formulas. And we want to see how those uncertainties carry through our calculation. That's called propagation of error or propagation of uncertainty. Here's a very simple example. We have two numbers A and B, and we want to find C. Well, you might guess you just add the uncertainties together, but that's not quite right. The uncertainty in C would be a little too large if you did that. The correct way is to use something called the root mean square or quadrature, where you add the uncertainties, square them, and then take the square root. In this case, the uncertainty is a little smaller than it was in that case. We can generalize that to a rule that you have to memorize. This rule is true for any combination of operations that are just addition or subtraction. It could be something as long as this guy, A plus B minus C plus D minus E. Well, the uncertainty in the measurement, delta F, is simply the sums of the squares of the uncertainties square rooted. Note, it's always a plus sign in these formulas. Okay? We'll be giving you some examples and some problems for you to use that rule. Another common rule is for multiplication and division. We're not showing you where these rules come from. They come from calculus and statistics. We'll show you how to do that later. If you have any combination of multiplication and division, say F equals A times B times C divided by D times E, that's a combination of multiplications and divisions, then all you say is the relative uncertainty, delta F over F, is equal to the sum of the squares of the relative uncertainties square rooted. And when you calculate this number, then delta F is found by multiplying the value of F by this relative uncertainty. We also have to work with functions, the natural log, the exponents, sine, and cos. And those take a bit more work, but what I want to focus your attention on this is down here. The uncertainty in any function is the uncertainty in the quantity you measure times the derivative of the function. Okay? That's the big rule we're using. Right? We always use quadrature to the result, and that makes sure that my answer will always be positive. Absolute uncertainties are always positive. In this formula, it's important to remember that A is the measured value, delta A is the uncertainty in the measurement, f of x is the function, and f prime of x is the derivative. I'll show you a page that has all the common derivatives for the functions that we use. Here's an example down here. Suppose f is equal to the natural log of 3.51 plus or minus 0.17. Well, the measurement value is a. The uncertainty is 0.17. The function is log or natural log of x, and the derivative, some of you may know this, is 1 over x. We can check this out in the table. Here's the function, there's the derivative. So delta f is the uncertainty in A times 1 over A, right? So that's 0.17 over 3.51, this number right here. So my result, the natural log of 3.51 is this number, plus or minus 0.0484. This starts with a 4, so we round this to 5, and we round this number to 1.26. Here's our several common cases that we would work with. One is the multiplication by a constant. Suppose the radius is half the diameter. Now, the function here is constant times x. And so delta f, according to our rule, will be the uncertainty in the measurement, which is x, times the derivative of this function. Well, the derivative of this function is just k. So delta f equals k delta x. Or for how this guy is written, it's delta r equals the constant 1/2 times the uncertainty in delta d. So if we look at d equals 5.6 plus or minus 0.2, then r is half this, and so is the uncertainty. Another common case is the square of a measurement. If a equals d squared, then we have to remember from our rules that this is the function f equals x squared, the power. So delta f equals the uncertainty in the measurement, which is x, times the derivative of the function. Go back to this table. And x squared, the derivative is, well, z is 2. 2 minus 1 is 1, so 2x. So here we are back here. So using the symbols up here, delta A is 2d times delta d. So if d is 5.00 plus or minus 0.05 centimeters, A is equal to 25.0 plus or minus 0.5 centimeters. I get the 0.5 from 2d, 2 times 5 is 10, times 0.05, that'll be 0.5. Last common case I want to mention is the square root. So the function would be f equals x to the half. Right? So delta f is delta x times f primed of x. Right? And the derivative of this function would be 1/2 x to the minus 1/2. Okay? Or this right here, delta x over 2 root x. So in terms of the symbols we start out with, delta A equals delta D, that's the measured quantity, over 2 root D. So if D is 25.0 plus or minus 0.2 centimeters squared, then the square root of this is 5. Right? But the uncertainty would be 0.2 over 2 times 5, or 0.02 centimeters.